This is a gentle introduction to TLA+, which is a logical formalism based on simple math useful to describe digital systems. In a nutshell, the main ideas are that of state and behavior, where a behavior is just a sequence of states, and the state is an assignment of mathematical values to one or more variables. So the system is described by a formula about behaviors. This formula should be true for all possible or correct behaviors. And we build these formulas combining init and next. Init is a formula to describe initial states, and next describes state transitions. Let's write a simple TLA plus specification using Visual Studio Code. I have installed a plugin for TLA plus, which has very nice documentation, so have a look. So now I can create a new file with the extension .tla. I'm calling it semaphore because I will make a trivial example, a traffic light. Now control space, I can get the template for a module properly formatted. I remove this extends close because we don't need external libraries. Instead, I go on declaring the only variable needed for the state of the semaphore, and I call it color. And then the very first formula by convention is called type OK and should express the expected values for the variables. In this case, I expect the variable to get one of the values in this set of 3 strings, red, green, and yellow. Now, when I hit Ctrl S and save the file, I have enabled this default action of parsing the module so that I can get a warning in case of syntax error. Another useful thing is to install LaTeX on your PC so that you can format the specification in PDF. This is the command, and you can configure a shortcut for it. And the system will create a text file, then a DVI, and finally a PDF, so that we can see the specification formatted in standard mathematical notation. Okay, let's go on starting the real specification, that is the formulas init and next. In fact, type OK, strictly speaking, is not part of the specification. Rather, it should be a logical consequence of it, meaning that it should hold in all states of all behaviors described by the spec. And we will let the system check it. So in it, it's easy. We may assume, we may expect, we may decide that initially the color should be red. This is quite arbitrary. We may also use the very same formula as type OK also to define init. In this way, we would introduce a tiny bit of non-determinism, but things won't change much. The next formula surely is more interesting, and usually it is expressed as logical disjunction or of a few alternatives that we call actions, and that represents different kinds of state transitions. Let's give them meaningful names. For example, turn green or turn yellow or turn red. Now, If I save, I get errors because these operators are not defined yet. Let's give them dummy definitions. So as to make the parser happy. And now it compiles. We can export it to PDF. Let me close this because I think there is a refresh issue. And here is our skeleton of specification. Of course, it's not complete yet because it is totally unconstrained, except for the initial state. In the other states, every possible value would be okay, and so this is quite useless. And in fact, I think the tool would refuse to process this kind of incomplete specification. Before completing the specification, a little note on notation. In TLA Plus, it's customary to use this slightly non-standard mathematical notation for logical connectives. So they are more like bulleted lists, and this helps when writing large formulas. Okay, so the actions. The actions are usually the logical conjunction and of a few conditions. Conditions about the current states are also called enabling conditions. For example, in the current state, we require the color to be red, and then in the next state, which we represent with color prime, we allow the color to turn green. So this is a relation between states that we are expressing, a formula about state pairs. Of course, the other tools are essentially the same. We just need to adjust the colors. So here we go from green to yellow, and from yellow back to red. And that's it. I think we can export to PDF. And this is our complete specification of a traffic light. So the state initially is red, and then it can turn green. From green we get to yellow, and finally back to red. Now it's time to use the model checker tool to explore all the possible behaviors described by our specification. This is the command to check the model. We need to create a model file that is a configuration in which we stick to standard names for the init and next formula. So now we can run the model checker. This is the report. Now it's not important to understand it. By the way, this is the output from which this report is generated, but there's more interesting visualization that we can enable by setting here in the extension preferences for TLA Plus this option. We are asking the system to create also a dot file. Dot is the format for the popular graph width library to visualize graphs. We are asking a file named after our model name, so semaphore dot. This deadlock option is completely unrelated. And in fact, the system created also this dot file, which we can preview here. And this is a very nice visual representation which at a glance gives us all the possible states and behaviors. I think there's no need to explain it. As a beginner, I like a lot this kind of visualization, although they do not scale to the billions of behaviors of real systems. Anyway, I still like to use the configuration here and put some constraint in order to limit the state space to be explored by the tool and still have nice, although partial, views on the system. Anyway, a safer approach is to let the system explore as many states as possible and add properties to check in order to better understand and better verify the correctness of the specification. We already have one such property and it's type OK. So now we can ask the system to check it while exploring the state space. Now, to double check it, we can make a mistake here. And I think the model checker should spot it. In fact, it says that invariant is violated, and what's more useful, it gives us a trace that is a sequence of states, actually the shortest sequence of states leading to a state where the invariant does not hold, where type OK is violated. This is very useful. A final note about temporal logic, which is actually the backbone of TLA+. Up to now, we have written only formulas about single states or state pairs, like the actions. But TLA Plus allows also to express formulas like this about whole behaviors, using operators of temporal logic like this box, pronounced always. So this is a temporal logic formula. Let's see it in PDF. It says that type OK holds always in each state of a behavior. And in fact, that's equivalent to this type OK invariant. We may express the very same condition directly in temporal logic, like this. And that's exactly what the system does for us, so that we are not expected to write these strange temporal operators. The behavior is exactly the same. In fact, the whole specification can be written directly in temporal logic like this, as the conjunction of init and always next. Here the only issue is that we need to add this strange reference to the variable color here. Let's see it in PDF. This is a technical detail not worth explaining here. It has to do with so-called stuttering steps. But this is the standard format of TLA Plus specification. And again, in fact, we could replace this with specification spec. And we should get, once again, the very same behavior. So temporal logic is behind the scenes, but the good news is that we don't need to know much about it in order to write useful specification. Just stick to init and next.